Before asking why the universe has laws, we must be very clear about what those laws actually are. When physicists speak of laws, they are not talking about commands or rules enforced by something outside the universe. There is no cosmic rule book, no external authority, no hidden judge making particles behave. Instead, the laws of physics are regularities, consistent patterns in how nature behaves. Consider something simple. A stone falls when released. Light bends near massive objects. Energy is conserved. These behaviors are not choices, they are reliable patterns. Physics does not explain why the stone falls, it explains how consistently it falls. This distinction matters deeply. Physics describes what nature does, not what nature should do. Newton did not create gravity. Einstein did not invent space-time curvature. They discovered mathematical descriptions that matched reality with astonishing precision. This means laws exist independently of humans. They work even where no one observes them. They apply everywhere we can measure. The same equations describe atoms, stars, entire galaxies. This universality is one of the greatest mysteries of science. Imagine a universe where gravity changed strength every second, electrons randomly altered their charge, time flowed differently each day. Such a universe could not form atoms, memory, structure, observers. Our universe is remarkably stable. The constants of nature, such as speed of light, strength of forces, mass of particles, appear fixed to extreme precision. This stability is not explained by the laws, it is assumed by them. At the most basic level, physics begins with an assumption. Nature behaves consistently. But physics cannot prove this assumption, it relies on it. This leads us to the first deep question. Why is the universe orderly rather than chaotic? Why does anything repeat at all? Now we ask something radical. Is it possible for a universe to exist without laws? A universe without laws would have no predictable behavior, no stable particles, no causality, no memory. Events would not follow from prior events. Nothing would persist long enough to be named. Such a universe would not merely be hostile to life, it would be hostile to existence itself. To have anything recognizable, the universe must support repetition, persistence, relationship between cause and effect. Atoms exist only because electrons obey fixed quantum rules. Forces have stable strengths. Space and time behave consistently. Remove the laws, and structure collapses. This leads to a subtle but important conclusion. A universe capable of existing in any meaningful way must be lawful. Here we encounter an unavoidable insight. We only observe universes that can be observed. This does not imply design, it implies selection. If a universe has no laws, no observers form, no questions are asked, no measurements exist. So lawless universes, if they exist at all, are invisible. Physicists call this reasoning the weak anthropic principle. It simply states the universe must allow observers, otherwise no observation occurs. This does not explain why laws exist, it explains why we see lawful ones. The deeper mystery remains untouched. Now we move beyond basics and into active scientific debate. Do the laws of physics exist from the beginning or emerge as the universe evolves? Traditionally, physicists believed laws are timeless. They existed even before matter. The universe follows them. Einstein strongly favored this view. He believed reality is governed by deep mathematical necessity. The universe could not be otherwise. This view suggests the universe is lawful because it must be. But this raises another question. Why these laws and not others? Modern cosmology offers a different picture. In the earliest moments after the Big Bang, forces were unified, symmetry dominated, distinctions did not yet exist. As the universe expanded and cooled, symmetry broke, forces separated, distinct laws appeared. In this view, laws are phase transitions, not imposed but settled into, like ice forming from water. High-energy experiments show laws change with energy scale. Forces merge at extreme temperatures. Constants may not be fundamental. This suggests what we call laws may be frozen remnants of early cosmic conditions. They feel eternal, but may not be. If laws emerge, then they are not absolute. They could have been different. They may evolve in regions we cannot observe. The universe may not obey laws. Laws may obey the universe. At some point, every serious physicist confronts a question that is both unsettling and unavoidable. Why does mathematics work at all? Not approximately, not metaphorically, but with astonishing precision. Many equations used in physics were developed with no physical purpose in mind. Examples: complex numbers, later essential to quantum mechanics; Riemannian geometry, later essential to general relativity; group theory, later essential to particle physics. These mathematical structures were explored for internal consistency, not for describing nature. Yet nature obeys them. This is not expected. This is deeply strange. Physicist Eugene Wigner famously described this mystery as the unreasonable effectiveness of mathematics in the natural sciences. Mathematics does not merely describe observations, it predicts entirely new phenomena. Examples: Dirac's equation predicted antimatter. Einstein's equations predicted gravitational waves. Maxwell's equations predicted radio waves. Reality seems to anticipate mathematics. Reference: Wigner, E., 1960. The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Physicists and philosophers propose three main possibilities. 1. Reality is mathematical. The universe is a mathematical structure. Everything physical is a manifestation of abstract relations. This view is strongly associated with Max Tegmark. Reference: Tegmark, M., 2014, Our Mathematical Universe. 2. Mathematics mirrors deep symmetry. Nature has symmetries. Mathematics is the language of symmetry. So mathematics works because symmetry is real, not numbers. Reference: Noer, E., 1918, Invariant Variation Problems. 3. Observer bias. We invent mathematics that matches what we observe. Unsuccessful mathematics is forgotten. This explains some effectiveness, but not predictive power. None of these explanations is universally accepted. Mathematics may not explain the universe. It may be that the universe and mathematics are not separate things. This idea will matter greatly later. Now we approach one of the most sensitive questions in physics. Are the laws of nature necessary or accidental? Certain constants appear finely balanced: strength of gravity, electron mass, cosmological constant, ratio of fundamental forces. If altered slightly, stars would not form, chemistry would collapse, long-lived structures would disappear. This is not philosophical speculation, it is computationally verified. Reference: Rees, M., 2000. Just 6 numbers. 3 possible explanations. A. Necessity. The laws could not be otherwise. There's a deeper theory forcing these values. This was Einstein's hope, but no such theory has yet been found. B. Chance. The laws are random outcomes. We live in a rare but permitted configuration. This explanation is mathematically loud, but deeply unsatisfying. C. Multiverse selection. Many universes exist with different laws. We observe the one compatible with observers. This idea is controversial, but grounded in inflationary theory. Reference: Weinberg, S., 1987. Anthropic Bound on the Cosmological Constant. The multiverse is not proposed to explain life. It emerges naturally from eternal inflation, string theory landscapes, and quantum cosmology. It is not philosophical invention, it is theoretical consequence. Still, it raises a disturbing implication. Laws may not be fundamental truths. They may be environmental facts. We now reach a frontier idea, rarely discussed outside research circles. What if laws themselves change? Physicist Lee Smolin proposed that laws may evolve across cosmic history. Universes may reproduce through black holes. Successful laws propagate. This is called cosmological natural selection. We know that forces unify at high energies. Constants depend on vacuum structure. Symmetry breaking determines behavior. This suggests laws are not eternal. They are frozen outcomes. At extreme scales, what we call laws may dissolve. Some quantum gravity models suggest time itself emerges. Causality is not fundamental. Laws appear only after space-time stabilizes. This is deeply counterintuitive, but supported by research in loop quantum gravity, causal set theory, emergent space-time models. Reference: Rovelli, C. 2004, Quantum Gravity. The universe may not obey laws. Instead, laws may be habits of the universe, stable but not absolute, reliable but not eternal. Laws of physics do not explain reality in the way we intuitively think they do. They describe, they predict, they correlate, but explanation is something else. Consider how physics often answers why questions. Why does an object fall? Because gravity acts according to an inverse square law. Why does gravity follow that law? Because space-time curvature behaves according to Einstein's equations. Why do Einstein's equations hold? Because they are consistent with observation and symmetry. At some point, explanation loops back on itself. Physics reaches a boundary where it says, this is simply how nature behaves. This is not a failure of physics. It is a limit of explanation. A crucial insight: laws do not cause events. They summarize regularities. The equation does not make the electron move. The electron moves, and the equation describes that motion. This overturns a common assumption that laws somehow govern reality. Instead, reality behaves, and laws are our compressed descriptions. Reference: Cartwright, N. 1983, How the Laws of Physics Lie. Physicist Paul Davies asked a sharp question. If laws govern the universe, what enforces the laws? Another law? A meta-law? An infinite regress? There is no place in physics where laws are applied. They are simply observed. This suggests something radical. The universe does not follow laws. Laws follow the universe. Now we reach the hardest question physics can ask. Could the universe have been otherwise? In philosophy and physics, a distinction is made. Necessary truths could not be otherwise. Contingent truths could have been different. Is gravity necessary? Is quantum mechanics inevitable? Is space-time unavoidable? Physics cannot currently answer this. Many physicists hope for a final theory where only one universe is mathematically consistent. Laws are forced by logical necessity. No free parameters remain. This is sometimes called the dream of inevitability. Einstein famously believed, "What really interests me is whether God had any choice." So far, physics has not found such inevitability. An alternative is deeply unsettling. Some facts may have no deeper explanation. They are not chosen, not designed, not derivable. They simply are. This includes why these laws, why existence, why anything at all. Philosopher Bertrand Russell summarized this bluntly. The universe is just there, and that's all. Physics does not refute this. Physics quietly allows it. Calling something a brute fact is not ignorance. It is recognizing the end of the explanatory chain. Every system, even mathematics, rests on axioms. At some level, explanation stops. Description remains. This may be unavoidable.
Now we question the question. Is why does the universe have laws even a meaningful question? To ask why assumes the thing could have been otherwise. A comparison makes sense. But what if lawfulness is inseparable from existence? A non-lawful universe is not a universe at all. Then the question collapses. Some physicists propose the universe exists because it is self-consistent. Inconsistent structures cannot exist. Laws are simply constraints of consistency. This is not design, not purpose, just logical stability. Reference: Hawking and Mladenov, L. 2010, The Grand Design. At the deepest level, physics may say the universe has laws because a lawless universe cannot exist long enough to be real. Not chosen, not imposed, not explained, simply inevitable. Physics can answer how laws behave, how they evolve, how they break. It may never answer why there is lawfulness at all, and that boundary may be permanent. Human minds did not arise outside the universe. They are products of the same laws they attempt to understand. This creates a loop.
Every thought you have is carried by electrical signals, obeys quantum mechanics, respects conservation laws, evolves according to thermodynamics. Even asking why the universe has laws is an event governed by those laws. This raises a subtle question. Are we discovering laws, or are lawful systems the only ones capable of discovery? Our brains evolved to detect regularity, pattern, cause and effect. A universe without stable laws would not allow memory, not allow prediction, not allow learning. So intelligence itself is biased toward lawfulness. This does not mean laws are invented. It means lawful universes produce law-seeking minds. Physics works by compressing reality into equations. An equation is a memory-efficient summary, a pattern extractor, a cognitive shortcut. Some physicists propose laws are the universe's most compressible features. Where compression fails, laws disappear. This connects physics to information theory, algorithmic complexity. Reference: Kolmogorov, 1965. 3 Approaches to the Quantitative Definition of Information. Increasingly, physicists suspect that information, not matter, may be fundamental. Physicist John Wheeler proposed, every physical quantity derives from information. Particles, forces, space-time, all emerge from binary distinctions. Yes, no, this, that, observed, unobserved. In this view, laws are not forces, they are constraints on information flow. For example, speed of light limits information transfer. Quantum uncertainty limits information precision. Entropy limits information storage. So laws define what information can exist, move, and persist. The second law of thermodynamics states entropy increases. But entropy is not disorder, it is missing information. The arrow of time itself may arise because information cannot be perfectly preserved. Thus, laws may be expressions of information loss. This reframes lawfulness not as control, but as limitation. Now we address a subtle but powerful idea. What if laws exist without doing anything? Structural realism claims objects are secondary, relations are primary, structure is real. Particles are not fundamental things, they are nodes in a relational network. Reference: Ladyman and Ross, 2007. Everything must go. Laws are invariants of structure. They do not govern, they persist. Like a triangle always has 3 sides, not because of enforcement, but because of definition. Similarly, a universe has laws because structure has constraints. No meta-laws, no enforcers, no cosmic authority, only consistency, stability, persistence. Laws are not applied, they are what remains unchanged. At first glance, quantum physics appears to destroy the idea of laws entirely. Events happen without cause. Outcomes are probabilistic. Certainty disappears. And yet quantum mechanics is one of the most precise law-based theories ever created. This is not a contradiction, it is a clue. In quantum mechanics, you cannot predict which decay will occur, but you can predict decay rates with extreme accuracy. You cannot know a particle's position exactly, but you can compute probability distributions perfectly. So randomness itself is constrained. The universe allows unpredictability, but only within rigid mathematical boundaries. This suggests that laws do not eliminate freedom, they may define its limits. A truly random universe is not just unpredictable, it is unrecognizable. Quantum events are random but not arbitrary. They follow conservation laws, symmetry constraints, statistical regularities. Arbitrariness would mean no distributions, no averages, no stability. That does not exist in physics. Thermodynamics emerged before atomic theory. It worked even when microscopic causes were unknown. This shows laws can exist without underlying determinism. Entropy increases regardless of particle details. So lawfulness may not depend on certainty, but on large-scale inevitability. Reference: Boltzmann, 1877, über die Beziehung zwischen dem zweiten Hauptsatze der mechanischen Wärmetheorie. Some interpretations suggest probability is not ignorance. Probability is ontological. Reality itself may be probabilistic. If true, then laws do not describe events, they describe propensities.
If there is one concept that repeatedly generates laws, it is symmetry. In physics, symmetry means something remains unchanged under transformation. Examples: physics works the same tomorrow as today, time symmetry. Physics works the same here as elsewhere, space symmetry. From these symmetries come laws. Emmy Noether proved something profound. Every continuous symmetry corresponds to a conservation law. Time symmetry, conservation of energy. Space symmetry, conservation of momentum. Rotational symmetry, conservation of angular momentum. Laws are not primary, symmetry is. Why should reality be symmetric? Why should nature care about invariance? Physics has no answer. Symmetry is observed, not explained. If symmetry explains law, then broken symmetry explains structure. A universe with perfect symmetry has no distinctions, no particles, no forces, no events. Nothing can happen. So symmetry must be broken for anything to exist. When symmetry breaks, forces separate, particles acquire mass, directions emerge, time gains an arrow. This suggests laws are scars left by broken symmetry. They are not ideal, they are historical. The Higgs field breaks symmetry, gives particles mass, determines what kind of universe exists. Without it, no atoms, no stars, no observers. So a single symmetry-breaking event shapes all lawfulness downstream. This changes how we think about laws. Most fundamental equations of physics are time-symmetric. They work the same, forward, backward. Newton's laws, Maxwell's equations, Schrödinger's equation. None of them contain a preferred direction of time. Yet we experience memory of the past, no memory of the future, irreversible processes. This mismatch is profound. The dominant explanation comes from thermodynamics. Entropy increases. But entropy increase is not a law imposed on time. It is a statistical consequence of initial conditions. If the universe began in a highly ordered state, then disorder becomes overwhelmingly likely. Time gains the direction. This implies time's arrow is not fundamental. It is a consequence of low entropy beginnings. Reference: Penrose R., 1989, The Emperor's New Mind. If time itself emerges, laws that assume time may not be fundamental. Causality may be approximate. Before and after may be secondary descriptions, so laws may depend on time, but time may depend on deeper constraints. This inverts the usual hierarchy. Causality feels unavoidable, cause, effect. But physics quietly undermines this intuition. Radioactive decay has no cause in quantum theory. We can say when it happens, how often it happens, but not why this decay happened now. This is not ignorance, it is built into the theory. In general relativity, space-time can curve, time ordering becomes local, now is observer-dependent. In extreme cases, closed time-like curves appear mathematically. Causality becomes ambiguous. Physics allows this, even if nature avoids it. Some quantum gravity approaches suggest causality arises only at large scales. Microscopic reality is acausal. Order emerges statistically. So, laws may not enforce causation. Causation may emerge from lawful regularities. Reference: Dowker, F. 2005. Causal Sets and the Deep Structure of Spacetime.
Relativity suggests a strange picture of reality. In the block universe, past, present, and future all exist. Time does not flow. The universe is a four-dimensional structure. Nothing happens. Everything is. In this picture, laws do not operate moment by moment. They constrain the entire space-time structure at once, like a crystal lattice, a geometric object. So laws are not dynamic rules, they are static constraints. Our experience is sequential. The universe may not be. Physics describes the structure. Consciousness experiences the slice. This tension is unresolved. An alternative view challenges the block universe. Some physicists argue reality is not objects, reality is events. Becoming is fundamental. The universe is not a static thing, it is ongoing activity. If reality is process, then laws are habits of becoming. Stability emerges from repetition. Change is primary. This aligns with quantum field theory, statistical mechanics, and non-equilibrium physics. Why these habits? Why stable repetition? Why persistence at all? The mystery deepens rather than resolves. At this depth, the idea of nothing collapses. What we casually call empty space is one of the most structured entities in physics. Classically, empty space has no properties. Nothing happens there. Quantum theory says otherwise. The vacuum has energy, fluctuates constantly, produces particle-antiparticle pairs, influences forces and mass. Nothingness obeys laws. The vacuum determines particle masses, force strengths, the stability of matter, the value of the cosmological constant. Different vacua determine different laws. This means laws may be properties of the vacuum state, not of the universe as a whole. Reference: Weinberg, S. 1989, The Cosmological Constant Problem. Empty space behaves like a polarizable medium, a field-filled structure, a dynamical entity. Fields exist even with no particles, so the most basic thing in physics is not matter, it is structure. This pushes the mystery deeper. Why isn't the vacuum truly empty? Quantum fields cannot be perfectly still. Heisenberg uncertainty ensures fluctuations never vanish. Zero energy is forbidden. This is not dynamical, it is kinematic. It arises from structure itself. The Casimir effect demonstrates vacuum fluctuations produce force. Empty space exerts pressure. Laws operate even without matter. This is experimentally verified. Reference: Casimir, H. B. G. 1948. On the attraction between two perfectly conducting plates. If vacuum structure determines particle behavior, then laws do not govern space. Space is the law-bearing entity. This reverses intuition. We now approach a strange idea. What if objects are secondary? In quantum field theory, Particles are excitations, fields are fundamental. Objects emerge from interactions. An electron is not a thing, it is a pattern. If everything is interaction, then laws describe stable interaction regimes, objects are temporary, structure persists. Reality becomes patterns all the way down. Persistence requires stability, constraint, regularity, which is exactly what laws express. So lawfulness may be the minimum condition for persistence. We discover laws, we write equations, we impose structure. But does nature care? Some philosophers argue laws are descriptions, not entities. Nature behaves, we label the behavior. This view is called Humean regularity. Reference: Lewis.D, 1973. Counterfactuals. If laws are mere summaries, why do they predict unknown phenomena? Why are they universal? Why do they compress reality so efficiently? Pure projection fails to explain this power. Many physicists adopt a hybrid view. Laws are discovered constraints, expressed in human language, grounded in objective structure, not invented, not imposed, interpreted. Even if laws exist, they rely on numbers, and those numbers appear arbitrary. The equations of physics do not fully specify reality. They require inputs: speed of light, Planck's constant, electron mass, strength of forces, cosmological constant. Change these slightly, and the universe changes completely. The laws remain. Reality does not. Observations suggest constants are stable across time and space, but small variation is not ruled out. Some theories predict slowly changing constants, spatial variation across cosmic scales. If true, laws may be fixed, but their parameters may drift. If constants are contingent, laws alone do not determine reality. Something deeper selects the values, but physics has no confirmed mechanism for this selection. Some physicists pursue a radical idea. What if the universe obeys the fewest laws possible? Instead of asking why there are laws, we ask, what is the minimal structure required for existence? This shifts focus from explanation to constraint. In this view, laws are not instructions, they are consistency requirements. If violated, contradictions arise, stable existence fails. So lawfulness may be the cost of being coherent. Some mathematical structures exist because they are internally consistent. No alternatives are possible. The universe may be one such structure. This is not purpose, not design, not intention, just consistency surviving. Now we reach a layer beneath law. Contradictory structures cannot exist. This is not physics, it is logic. A universe that violates its own constraints cannot persist even conceptually. Perturb it slightly, it returns to itself. Some physicists propose laws are fixed points of cosmic consistency. Once formed, they lock in. No chooser is needed, no selector, no enforcer, only structures that collapse and structures that persist. Lawful universes persist. To exist is to persist, be distinguishable, interact, be identifiable. Each requirement implies constraint. Constraint implies regularity. Regularity implies law. Law is not added to existence. Law is existence. A thing exists because it behaves consistently enough to be a thing. This does not answer why these laws, why this structure, why existence itself. It only reframes the problem. The mystery survives intact. If all configurations were equally possible, chaos would dominate. But it doesn't. Reality is remarkably stable. In physics, most arrangements collapse quickly, disintegrate, fail to repeat. Stable atoms are rare.
Stable nuclei are rarer. Stable stars occupy narrow conditions. This suggests existence is selective, not generous. In dynamical systems, instability is common. Small changes amplify. Divergence dominates. Stability requires constraints, feedback, balance, which means stability itself is an achievement. Laws limit what can vary, how fast it can change, which configurations survive. They narrow possibility space. Without them, everything changes too fast. Nothing persists. Structure dissolves. So lawfulness may exist because stability demands restriction. Even stability may not be permanent. Current measurements suggest our vacuum may not be the lowest energy state. A deeper vacuum could exist. Transition would destroy known physics. This is not speculation. It follows from particle physics data. Reference: Degrassi et al. 2012, Higgs mass and vacuum stability. If true, laws are not eternal. They persist for long durations, then abruptly fail. This reframes laws as long-lived patterns, not absolutes. Even temporary laws can produce galaxies, life, thought, inquiry. Eternity is not required. Duration is. Physics strongly favors decay. Local order exists, but only by exporting disorder elsewhere. Every structure is borrowed. Every law-bound system consumes gradients, produces entropy, moves toward dissolution. This is unavoidable. Laws do not prevent collapse, they regulate it. Decay follows rules. Dissolution has structure. Even death obeys equations. Creation requires precision. Destruction requires almost nothing. This asymmetry ensures few lawful structures arise. Many fail. Survivors dominate observation. So lawfulness may be what remains after everything else disappears. We observe laws because lawless configurations vanish. Only stable patterns endure. Persistence selects regularity. This is not anthropic, it is physical selection. Nothing enforces the laws. Configurations that violate stability collapse, disappear, leave no trace. What remains looks lawful because it had to. Physics allows us to imagine countless possible universes, but imagination is cheap, existence is not. Mathematically, many universes are conceivable, with unstable particles, with runaway forces, with no persistent structures, with no time-like order. These universes are not forbidden, they're simply non-viable. They dissolve before anything can happen. To exist, a universe must maintain internal consistency, resist immediate collapse, allow repetition, support persistence. Lawfulness is not optional here. It is the entry cost to reality. From inside a surviving universe, lawfulness looks intentional, but survival can produce the same appearance as purpose. What we observe is not the average universe, it is the rare, stable one. Some physicists suggest everything mathematically consistent exists, but consistency alone is insufficient. A structure can be consistent and still contain no time, allow no evolution, permit no observation. Such worlds exist only abstractly, they never become. To resemble a universe, a structure must support change, preserve information, allow causally linked events. Lawfulness bridges mathematics and reality. It turns static consistency into lived structure. This leads to a subtle reframing. There is no cosmic selection committee. Instead, unstable configurations vanish, stable ones persist. Persistence accumulates structure. What survives becomes the universe. Why this explains laws without explaining origin. This view explains why laws appear universal, why regularity dominates, why chaos is limited. But it does not explain why existence happens at all, why anything passes the filter, why there is a filter to begin with. The deepest mystery remains intact. From within a lawful universe, laws feel necessary. Structure feels unavoidable. Reality feels stable. But this may be perspective, not truth. From inside, this universe feels inevitable. From outside, It may be one fragile outcome among many failures. Physics cannot step outside reality, it can only infer. At this depth, equations still work, but explanation thins. Not because we lack intelligence, but because some questions may not reduce further. Physics can tell us how laws behave, how they emerge, how they constrain, how they may fail. Physics cannot tell us why existence occurs, why there is something rather than nothing, why lawfulness appears at all. This is not defeat, it is honesty. So we return to the question, why does the universe have laws at all? And the most careful answer physics offers is not a sentence, but a posture. The universe is lawful because only lawfulness persists. Not because it was chosen, not because it was required, but because instability leaves no trace. And within that persistence, questions arise, including this one. If this question stayed with you, if you felt it deepen rather than resolve, if you enjoy exploring where physics meets silence, I invite you to subscribe to The Wandering Neuron, a place for slow thinking, deep questions, and calm journeys through psychology, philosophy, and the structure of reality. No rush, no noise, just wandering together.